welcome to another video from Tech Talk with Balu. Today, we're diving into the architecture of trust. We are going to look under the hood at the kind of software that runs things we trust with our lives and find out how it's engineered to never ever fail. To really get why this matters, let's start with a pretty scary thought. You're driving down the highway and the software that runs everything in your car just stops. What breaks first? Your anti-lock brakes gone, the sensors for your airbags are offline, your power steering is dead. In these critical systems, failure just isn't an option. So how on earth do you build software that's basically immortal? So that's the core challenge right there. We're talking about software in medical devices, in planes, and in our cars. It's just not allowed to crash. The system has to stay up and running no matter what. The whole idea behind this is a principle called high availability, and here's the key thing. It's not about preventing every single bug or error. That's impossible. Instead, it's about building a system that's smart enough to know when it's sick, heal itself, and just keep on going, often without a human ever even knowing something went wrong. Ooh, mind-blowing. Okay, so how do they actually pull this off? Let's look at the blueprint for a system that's designed to be uncrashable. We are going to use a real-world example, the QNX operating system, which is the secret engine inside tons of critical devices you probably use every single day. Alright, so it all starts with the fundamental design. A traditional system has what's called a monolithic kernel. Think of it like an old wooden ship. It's basically one giant piece. If you get one hole in the hull, the whole thing goes down. QNX, on the other hand, uses a microkernel. This is way more like a modern battleship. It's made of many small sealed, watertight compartments. If one part gets hit, you can seal it off, and the rest of the ship just keeps sailing. And this is a perfect illustration of that battleship design. See that tiny little box at the very core? That's the microkernel. It does almost nothing, just absolute basics. Everything else, your drivers, your apps, your file systems, they are all in their own separate self-contained processes. They're all individual watertight compartments. And that right there is the whole secret sauce. Because every single function is its own little program. If one of them breaks, it doesn't sink the ship. You just restart that one broken part. So, how does the system really build on this? It's not enough to just be able to restart things. You have to build a fortress around each part, so if one component goes rogue, it can't take anything else down with it. Now this is where it gets really clever, because it completely flips how most operating systems work. Normally, a buggy driver can bring down your entire computer, right? Blue screen of death, anybody? Here, a driver is just another program. It has its own little bubble of protected memory. So if your graphics driver has a bug and crashes, who cares? It can't touch the kernel. It can't touch the audio driver. You just kill that one process and restart it, all without booting or rebooting the machine. So you're probably wondering, how do all these separate parts then talk to each other? They use something called resource managers. The best way to think of these is like a really smart old school telephone operator. When an app wants to access some hardware, it doesn't call the driver directly. It calls the operator, the resource manager, who then patches the call through to the right place. And because you've got this central operator, you can pull off some amazing tricks. For instance, you can have a backup or shadow process running in the background. If the main one fails, the operator just instantly starts sending all the calls to the backup. The apps on the other end of the line have no idea anything even happened. You can even upgrade software on a live system this way. You just start the new version and tell the operator, hey, send all new calls over here now. So we've got a system with isolated parts, protected parts, and restartable parts. That's all great passive defense. But what about actively monitoring the health of the system? What happens when something actually goes wrong? Who is the first responder? That is the job of the High Availability Manager, or HAM for short. If that microkernel design is somebody's body armor, the ham is its own personal paramedic, always on call, always watching every vital sign. And the logic the ham uses is brilliantly simple. First, you tell it about the entities. These are the patients, the critical programs you need it to watch. Second, you define the conditions. These are the symptoms it should look for. Did this process just die? Or did it miss its regular heartbeat check-in? And finally, you specify the actions. That's the treatment plan, like what the command to run to bring that process back to life. And what's so cool is how this is all organized. It's not some complex database. It's just a set of folders and files just like you have on your own computer. Every critical process gets a folder. Inside that, there's a folder for symptoms to watch, like death. And inside that, a file for treatment, like restart. It's basically a set of simple, clear medical charts for every piece of software. So what this all boils down to is that a developer can set up these really sophisticated recovery plans with a simple command, a line of code like this. It's basically just a note left for the paramedic. It says, hey, keep an eye on this process. If it dies, I need you to immediately run this exact command to revive it. Simple as that. Alright, let's zoom back out. We've gone through microkernels and memory protection and these ham paramedics, but all these technical details, they're not really just about clever engineering. They're about building the foundation for trust in the technology that's all around us. So if there is one thing to take away, it's how these layers all work together to build that trust. The microkernel isolates a failure. The memory protection contains it so it can't spread. And the high availability manager actively swoops in to heal the system. That's it. Isolate, contain, heal. That's the architecture of trust. And now that leaves us with one last big question to think about. Oh, it's pretty easy to design a system that works perfectly when everything is going right. The real challenge, the one that matters more and more every day, to build systems that are designed to handle failure gracefully. So the question we have to ask ourselves is, are we just designing for success, or are we truly building for resilience? Thank you for watching. Hope you've enjoyed this video and learned something new. If you did, please feel free to drop a like and subscribe to this channel. Thank you and see you in a bit.